Hello everyone, my name is Tišljarič and I will present you the paper entitled Spatiotemporal Traffic Anomaly Detection on Urban Road Networks using Tensor Decomposition method. This research is performed on the Center of Research Excellence for Data Science and Advanced Cooperative System in Zagreb, Croatia. We have two institutions that participated in this research. So first one is Faculty of Transport and Traffic Science at University of Zagreb, Croatia, and second one is the Laboratory of Artificial Intelligence and Decision Support at Institute for Systems and Computer Engineering, Technology and Science, University of Porto in Portugal. So the content of this presentation is divided in standard way, so we will give some kind of introduction and motivation for this research. We will talk about the used methodology and we will cover the results and at the end conclude. So in this paper we propose the usage of the speed transition matrix. It is the novel traffic data representation. So the main question is how the speed transition matrices can be used for the traffic anomaly detection. So first of all, we need to define the anomaly detection method, and then we have interest in finding where and when does the traffic anomaly appears on the traffic road network in urban centers. The primary motivation for this study is to detect the potentially dangerous road segments. The secondary one is the estimation of road traffic state. It's important to identify the hotspots of the congestions, and it's very useful for the routing services. Also, infrastructure maintenance authorities have the use of this kind of application. When expanding or building the new road, or changing the signalization on existing one, or for the analysis before and after building the new road. The methodology used for this research is divided into three parts. So first one is related to data preprocessing, then we have the speed transition matrix generation and the anomaly detection method. So in next slides we will go through these steps. For the data we use the classical GPS data, so we have a large data set of GPS coordinates that are map matched. So in time interval from 2009 to 2014 there were approximately 4,200 vehicles, mostly taxi and delivery vehicles. Data is provided by the company called Joaõ during the Sordito project. To get better performance, we excluded some data from our dataset. So first of all, we partitioned the data by the season, so we excluded summer months, July and August. This picture on the right, the upper picture, shows the speed profiles for the city of Zagreb for the summer months and rest of the year period. We can see that summer months have significantly larger speeds in rush hours. Why? Because there are not a lot of vehicles in the city, because a lot of people go to holidays. The similar pattern can be seen on the picture below for working and weekend days. So at weekends we have significantly larger speeds and we don't have speed drops at the rush hours. So we excluded also the weekend data. To be more precise, we divided our dataset into 8 time intervals. First two shows the intervals between the morning rush hour, third one shows the morning rush hour, fourth one shows the period between rush hours, fifth one shows the evening rush hour, and 6, 7 and 8 shows the intervals after the evening rush hour. So let's explain the speed transition matrix. First, let's define the transition. In this paper, we define transition as movement of the vehicles between two links on the network. So for example, on this simple graph, if you're traveling between the vertices V1 and V4, you will have two transitions. So first one would be E1 to E2 and second one from E2 to E4. So let's look at this transition E2, E4. So we can say that this first one is the origin link and the second one is destination link for this transition. Then we will take the average speed on the origin link and the average speed on the destination link. With those two values, we can construct this kind of matrix. So this matrix represents data for one transition in one time interval. We mentioned eight time intervals in past slide. So for one time interval, we get the empty matrix. Then we count the speed transitions between the origin speed, so average speed on the origin link, and the average speed on the destination link. So this matrix will show us the count of speed transitions for one transition in one time interval. On this example, we can see that 208 vehicles had the origin speed 65 and destination speed 60. To take another example, only 10 vehicles had origin speed 55 and the destination speed 30. Then this number of vehicles or frequency we can transform to the probability. Then we get the final form of the speed transition matrix. So speed transition matrix show us the speed probability distribution when vehicles are traveling between the two road segments, so one transition in the observed time interval. So how can we explain those values inside the matrices? So on this left image, we can see, let's say, normal traffic behavior. Why? Because the speeds on the origin and destination links on this transition in this time interval is relatively high. So we don't have any congestions. On this other picture, we can see that on this interval, on same transition, we have a lot of vehicles that had very low origin speed and very low destination speed. So we can see that this is some kind of the anomaly and serious congestion. Now we will explain how we constructed the tensors. So first step was to extract the speed transition matrices. Then every matrix was flattened in vector. Then those vectors are placed in one matrix with dimensions m times n. So m will represent the length of flattened speed transition matrix. In our case, it will be always 400. And the n will represent the number of transitions that are observed. T will represent the time intervals, so in our case 8. As we can see on this picture, the n is fixed to 100. That means that every tensor represents the 100 transitions. We use the number 100 because in that way we take the part of the transport network and not the whole. We did that to extract more diverse traffic patterns that are maybe special for some part of the network. If we use only one large tensor, those kind of information could be lost. So let's say a few words about the tensor decomposition. We use the non-negative parafac method. We already described the input tensors. Then we applied the non-negative decomposition. As the results of the decomposition, we get three vector matrices. So first one, A, will represent the characteristic speed transition matrices, so it will give us the traffic patterns. Second one, B, will show us the spatial characteristics for every transition. So in other words, we will see which road segment characteristic matrix describe the best. And for C, we get the temporal characteristics for every time interval, or in other words, we will get the answer which interval characteristic matrix describe the best. This is the anomaly detection concept. So we need to define some kind of the measure of the anomaly. So some kind of difference between normal behavior and anomalous one. To represent the normal traffic behavior, we use the average speed transition matrix, and then we measure the difference between each characteristic matrix and the normal behavior. So for measuring this distance, we use the Kullback-Leibler divergence. It measures the relative entropy. So basically we chose this metric because it measures the difference between two probability distributions, and the speed transition matrix is some kind of probability distribution. This is the used algorithm. So for every extracted tensor, we applied the non-negative tensor decomposition method to extract the characteristic matrices. Then we applied Kullback-Leibler divergence metric in order to measure the difference between every characteristic matrix and the average characteristic matrix that represents the normal traffic behavior. Then we will use the standard interquartile range measure, also called the Tukey's fences, to detect the anomalies. So if the distance is larger than the expression under number 3, the characteristic matrix will represent the anomaly. Here are some examples of the extracted traffic patterns and their corresponding temporal components. This first one shows us the normal traffic behavior, and if we look at its temporal component, we can see that this behavior is normal for the morning time intervals, interval in between the rush hours, and in some extent at the evening time interval. If we look at example A3, we can see the matrix that represents relatively fast traffic. So it's also normal for the morning time interval when there are no vehicles on the roads. And a last example shows us the anomaly. So we can see that large amount of vehicles had the origin and destination speeds very, very low. So it's characteristic behavior for the morning and evening rush hours. And if we look at its Kullback-Leibler divergence value, we can see that this example have the highest one. We will show two kinds of results. So first group shows the, let's say, expected anomalies. So anomalies that happens in the rush hours. And second one are unusual anomalies, so the ones that happen in some other time intervals. For example, we can see that this pattern is happening before the morning rush hour, and we will see why in next slides. So these are examples for the most anomalous patterns. We can see that all of those have very similar pattern, so the both origin and destination speeds are very low, and the temporal components show us that these kind of anomalies are normal for the morning and evening rush hours when the congestions are the largest. But on the other hand, we can see the examples for the unusual anomalous patterns. So we can see the patterns are the same, so very low speeds on origin and destination links, but the temporal components show us that those serious congestions do not happen at the rush hours. For example, this pattern will occur between the rush hours and at the evening. And those three examples are characteristic for early in the morning before the morning rush hour. So in this slide we represent the spatial characteristics of 5 most anomalous transitions colored with red. So 1, 2, 3, 4 and 5. And the green ones shows us the unusual traffic anomalies. If we look at the expected anomalies, we can identify, let's say, 3 hotspots. First one is here on indexes 1 and 2. Here is the business area of Zagreb. 3 and 4 will show us the traffic pattern for one of the most congested bridges in Zagreb, and the 5th one will show us the city center. So the unusual ones are mostly located at the edges of the city, and we can say that most of those patterns occurs very early in the morning. So we captured the patterns, the people that are traveling to the city for the work. And those 2 ones in the city center can be related to the nightlife or some kind of touristic attractions at the evening. So to conclude, we present the method for the traffic anomaly detection in the urban road network, and we proposed the novel traffic representation method called speed transition matrix. Method can be used to detect the spatiotemporal anomalies on the road traffic segments, or to detect some kind of unusual, suspicious anomalous traffic patterns. In our case, that was the ones that do not occur at the rush hours. The results present the valuable traffic information that can be useful for, firstly, for routing application, responsible urban planners, or for the road infrastructure maintenance authorities. Thank you. I will be happy to answer any of your questions. If you will have additional one, you can contact me on this mail.